So yesterday we have discussed the symmetry operations and their relation with the space and time. Now today we will discuss in detail. So yesterday we found that the normal geometrical symmetry operations are translation or displacement, then rotations, then inversion in space and time. So these are the geometrical symmetry operations, and we said that the translation symmetry is due to the fact that space is homogeneous and time is also homogeneous. Space and time are homogeneous. So as an example, I said you perform one experiment in Kerala and another experiment in New Delhi or in some other part of the world. You should get the same result with some local parameters affecting the result. That we can explain. Normally, we should get the same result. That is the one of the basis of science. Okay, scientific facts is same for all. Entire universe it is same. No conflict. Maybe conflict comes at some initial stage, but after some time, everything will settle down and everybody will agree with one fact. That is the importance of science. So you do some experiment in both many places in Earth on Earth. So we should get the same result. So we know that Earth is a curved one, curvature, because Earth is a sphere. So some people are standing in one direction and another people are standing in some other direction. But whatever it is, the gravitational field of the Earth is there, magnetic field is there. So whatever be the reasons, we should get the same result with within some given error. Okay, that is how science progresses. So whatever you discover in America is valid in India. Okay, and whatever you discover in India is valid in Russia. Every place it is same result. Local some parameters can affect, but that you can find the reason for that. Okay, so since space is homogeneous, the Hamiltonian of the physical system is invariant, have no change when you perform a translation in space. You have a system, so you are simply translating the system in space, so the Hamiltonian remains invariant. So that is known as translation invariance. So I will write all this. So we have we will start with the yesterday we have already discussed the dynamical symmetry and degeneracy connection between them. Now we will discuss the geometrical symmetries. Geometrical symmetries like translation, okay, translation, then comma, rotation, okay, then inversion in space. Okay. Also in time, there is no rotation in time, but translation in time is there. Space, and we can say translation in time. Okay. So there is no rotation in time. There is no inversion in time. So you cannot get the, because that is an anti-unitary operator. You will not. You can go. You cannot go to the past. So only translation in space. Sorry, in space and time. Then rotation and inversion in space. These are the geometrical symmetry operations. Okay. So the example of these are, the reason for this symmetry is space is homogeneous. Okay. Space is homogeneous. So what? So when you do an experiment in Kerala or in New Delhi, you should get the same result. Okay. Because space is homogeneous. So due to this reason, the Hamiltonian H of a physical system, we have found yesterday, Hamiltonian of a physical system remains invariant under translation in space, during translation in space. Okay. So if the system has no change, we say translation invariance. And that implies, if translation invariance is there, today we will show that implies conservation of momentum, linear momentum, P equal to mv. So translation of translation of system over the space, the Hamiltonian remains invariant, and that leads to conservation of momentum, linear momentum. And the fundamental reason for this is homogeneity of space. Okay. Another example is, we will discuss each one by one. Okay. So another example is, first is homogeneity of space, then isotropy of space. So in whatever direction you look, space looks same. Okay. Same property in all directions. Same property in all directions, that is known as isotropy. So isotropy of space leads to the rotational symmetry. Okay. So homogeneity of space leads to the translation symmetry, and Isotropy of space leads to the rotational symmetry and hence the conservation of angular momentum. Okay, so this implies conservation of angular momentum. Conservation of angular momentum. And one more thing is uh, homogeneity in time. Time is also homogeneous. So what? So when you do an experiment at same place in your laboratory, maybe in your laboratory today or tomorrow, or you should have performed yesterday, at any time, any instant of time, you should get the same result. No change for the result. Maybe some error is there within given error. Error is allowed. Error is allowed in all experiments, experimental measurements. Some error is there. Error should be there. Okay, error is a must. So within the given error, your results or your inference is always same. So at whatever time you do an experiment. So these two, so that will lead to the conservation of energy. So time homogeneity in time leads to the conservation of energy. So this is what I told you yesterday, the connection between our superstitions and beliefs when you compare with the scientific principles. So somebody say that this time is better for marriage or some our normal things, but science says all time are same. When you do some process or experiment, all the instants are same. Also, there is no preferred direction. Somebody say that you pray looking at the east direction, but science says all directions are same because it is isotropic. So that doesn't make any difference. According to science, you pray into any direction, that is same, gives same result. So now we will discuss in detail the first idea. Each idea we will discuss, these all three idea. So today we will discuss the first idea only, that is translation in space, which leads to conservation of linear momentum. Okay, that is today we are going to perform. We are going to prove from simple principles of quantum mechanics. We are going to show that this, since space is homogeneous, translation in space, it possesses symmetry and therefore P will be conserved, linear momentum will be conserved. So as I said, we have discussed in the last chapter, we can consider this in two point of view. One is active point of view and another is passive point of view. Since we have discussed this idea, I am not discussing it again. Active means, passive means, what is passive? Coordinate is moving, system is fixed. and just the reverse is the active point of view, which we normally do active point of view. Coordinate is fixed and system is moving. Okay, so we are considering only the any way you can consider, result is same. That is according to your convenience and experience, you can do any point of view. So we are considering active point of view. Okay, because we are more familiar with active point of view. So you consider the a system. Okay, we have the x, y, and z axis. This is x, y, and z axis. Then consider the particle at point P. Okay, so let initially the particle was at point P, sorry, P dash. Okay, then after translation, let it reaches, that it moves along the x direction only for simplicity. So it finally it reaches the point P. Okay, so the initial position vector is this one, final position vector is this one, and we are doing an infinitesimal translation. So that is this one. Let us call this infinitesimal translation as delta rho. Delta rho. Okay, so this is delta rho. So when you add this vector with this vector, you get the final vector. Simple vector addition. So you can call this vector as r minus delta rho. So r minus delta rho, when you add with delta rho, you get r. So this is vector r. So this is vector delta rho, and this is r minus delta rho. I think it is clear. Or I can draw a bigger figure. So r minus delta rho plus delta rho gives r. Okay. So the particle was initially at point P dash. After translation, it becomes at P. Or you can consider in the reverse also. Initially, it was in the point P, then it moves to P dash. Anyhow, you can consider. Okay. Now, let this translation, infinitesimal translation delta rho, is performed by a Hermitian operator, alpha. So who is doing this translation? Operator alpha. So alpha is performing this translation. This is the Hermitian operator. So alpha is the Hermitian operator. Comma, which generates what it does? Infinitesimal displacement. Infinitesimal translation or displacement along the x-axis. That is, we call it as delta rho, vector delta rho of the system. So this is the operator alpha. Okay. Now, so corresponding to every Hermitian operator, we can write a unitary operator. So what is that unitary operator? So the unitary operator corresponding to alpha. So unitary operator generated by alpha, corresponding to alpha, is, we can call it as U alpha. And what is its job? It is doing a delta rho translation. Okay, so this is how we can represent U alpha. So alpha generates U, so we call U alpha, and it does a translation delta rho. Okay, so this can be represented as U alpha. You can write it as, yesterday we have seen e to the power of, also in last chapter also we have seen either e to the power of plus or e to the power of minus, whatever you can choose, e to the power of I into epsilon alpha actually. So here epsilon becomes delta rho. So that is a vector. So dot, if this is a vector, we have to write alpha as a operator or vector operator. So dot product. So e to the power of I epsilon alpha. Sorry, instead of epsilon we have delta rho. Epsilon is a very small quantity. So here epsilon becomes delta rho. Okay. So this can be written as we said earlier, this can be exponential, can be expanded as 1 plus I into delta rho dot alpha plus etc. Neglect the higher terms. Okay. So here U is performing this transformation. Unitary operator, U is unitary operator. You can perform any transformation. Okay. So we can write, suppose psi is the wave function at the point R. Okay. So we can say that, we can write it as, consider the initial wave function. Okay. Or final, anyway, anyhow you can take it as initial or final. So psi of, here actually R is final. Initial is R minus delta rho. Psi of initial position vector and final position vector. You can take this one as initial, this one as final, or this one as initial, or this one as final, no problem. So on the exponential sign changes, plus becomes minus, like that. Okay. So we can write, consider the wave function, initial wave function, psi of R. Okay. Then we can assume that, you can write that this U acting on U alpha delta rho acting on psi of R. What is the result? That is the new wave function, psi dash of R. Okay, which is the psi of final wave function, that is r minus delta rho. So that means this is initial and this is final. So this equation is written in such a way that this is initial and this is final. Anyhow, anyway you can take, no problem. So u is acting on psi of r, you get the final wave function. Okay, is that clear? Or you can take in the reverse also, reverse way also you can take, no problem. Okay, is that clear? So this means that, what is the meaning of this one? This means that the wave function at r is same as wave function at r minus delta rho. Wave function is same, or we can say that wave function has maximum value at r and r dash, or p and p dash. Wave function is same at p and p dash. So this meeting is over, so I am closing.